In this tutorial, we are going to complete the digital link where we're actually going to demodulate the signal and recover the original bit stream, compare it to the original bit stream, measure the bit error rate, and see how the error rate depends on the signal to noise ratio in the channel, or in our case, the noise level. To begin, what we're going to do is open up tutorial number 5. Recall that we have a multipath channel. In the multipath channel, we're actually going to make sure that the multipath channel doesn't do much. So we're going to set the bulk delay to 0, the gain of the multipath to 0. We're going to investigate the effects of additive noise in this simulation. Let's clean up the topology a little bit. We're going to move the data block at the corner, move the coder a little bit to the left, free up some space for some other blocks. We're going to take the multipath and move it. And now we have, in between the multipath and the receiver, for the receiver we have a Nyquist square root Nyquist filter, which acts as the match filter at the receiver. What we are going to do is insert the add noise block in order to model noise in the channel or at the receiver. Let's move this block here. So now we have the add noise, we have the receiver, which is the Nyquist square root filter, which acts as the match filter as we discussed. Let's move this block closer to the add noise, move the eye diagram also. And let's go ahead and change the noise level to about 0.2, the variance. Let's save this as tutorial number 6 and run a simulation. We'll see that the eye diagram is actually closed a little bit due to the additive noise. We don't have any multipath effect because we basically set the multipath gain to 0. In order to demodulate the received signals, notice that after a match filtering, we have to sample the filtered signal at the peak and take the sampled values at the peak only and discard all the other samples. Therefore, we have to actually do a sampling and a sampling rate reduction, a decimation. After we do that, we have to then pass the samples through a slicer or a decision and then recover the original bipolar signal plus or minus 1 and compare it to the original one to get the bit error. So that's what we're going to do in the following steps. So the first thing we're going to do is go ahead and grab this block called Demux. This is a very useful block, very powerful block. The Demux block actually takes, let's go ahead and connect it. The Demux block actually takes the input sample stream and demultiplexes it to the output streams depending on how many are connected to it. So for example, you can take the input stream and split it off into various other streams, and in each case, of course, you might achieve a downward downsampling. Now the Demux block has a parameter, a couple of parameters. One is the ratio of the input rate to the output rate. Now recall that we oversampled the bits by a factor of 8, and the Demux, we basically specify 8 as the ratio of the input rate to the output rate. So we're actually doing a decimation by a factor of 8 to recover the original bit stream. The second parameter is also very important, and it's a type of parameter called an array. And you will run into these kind of parameters. They're very interesting because you can actually specify an array length, in our case 1, which indicates that we're only going to have one output stream, and then the phase that we're going to use to sample the input stream. If we had multiple outputs, then we would have, like for example, if we had 2, then we'd have the array length of 2, and for each stream we would specify the phase or the sampling phase for that particular stream. In this case we have one stream and the phase is going to be 0. It turns out to be, the 0 phase turns out to be exactly where the match filter peaks. Okay? Now, the next block that we need to add is called the slice block. Now we can just go ahead and type it in or select it from the list. We'll just go ahead and type it in. and it's going to follow the demux. The slice block is actually going to take the samples of the match filter and then perform a decision on them. In our case, the decision being, because we are ascending bipolar, whether it's greater or less than 0. So the slicer is actually between plus and minus 1. Let's go ahead and connect these two up. Let's also save the topology. Now the slicer itself, and by the way, in order to see the rest of the topology, we can actually use the scroll bar at the bottom to move around. So let's go ahead and open up some space here. What I'm interested in doing is actually putting a plot, a time domain plot, after the slicer so we can see it in the time domain. Therefore, let's go ahead and grab that star. So just type in plot. Plot is actually a probe, or can be used as an individual block. Now, when you add a probe, automatically a random name is generated, because this has to do with the way probes are handled. And this random name is generated in order not to conflict, but it's easy to actually rename that. So let's go ahead and rename this block. Also show you how to rename a block. Now it's very important that this probe block not start with the name of the probe. So we'll call it X plot 0 in this case. That'll actually use less real estate. Let's go ahead and connect an output. Save our simulation. Now we're going to be able to actually plot the results of the slicing or the decision, and this is going to be at the same rate as the original bits that are generated. Now one other thing we need to do, and that is I'm going to insert a probe here, which is a plot probe. We're going to look at this in the time domain. Let's go ahead and change its parameters and set it to demux as a title. And what we're going to do here is look at the demux pulses. We'll see that the rate, the number of samples, is actually 1/8 the number of samples coming into the eye diagram, coming out of the eye diagram over here. And the reason we want to look at that is to make sure that we're sampling at the opening of the eye, right at the maximum of the match filter, before we do the decision making. All right, so let's go ahead and run a couple of simulations. First of all, let's check our noise. Let's make sure that we have actually absolutely no noise. And let's run a simulation. Now, we're running the simulation and we get a message down here that says improper parameters. The reason for that is we haven't set the parameters for the slicer. Now this slicer or decision block is very powerful in the sense that it's flexible and can be used to demodulate multi-level modulations. Since we only have 2 levels, we need to, this is an array parameter again, so you specify 2 as a number of levels, and then specify the 2 levels, -1 and 1, as the decision levels. Let's go ahead and save this. Now when we run, we're not going to get this complaint. We'll actually see some results. This is the output of the slicer, and you'll see that its values range from -1 to +1, and it's actually bipolar signal. And notice that it goes up to about 128 points. The demux is also sliced. It looks sliced, but it's not. These are actually samples of the output of the match filter, and they happen to be, in this case, right at the eye opening here, and correspond to the value that you see here. As you can see, it tracks it very well. So our phase is absolutely correct, and we're sampling right at the maximum of the match filter, which is where you want to sample in the digital link. So everything checks out over here. We got a wide open eye. Let's go ahead and delete these plots, save the results, and let's go and change the noise. Let's change it a little bit, add some noise. So let's put in a factor of like 0.2. Run. Now you'll notice the effect of the noise, and the noise does affect the demux output because the eye is obviously changing. The time domain waveform is changing here, and then we're sampling that. But notice that the slicer output, of course, is always going to be plus and -1 because these are based on the decisions. Of course, the eye is closing a little bit because of the additive noise. Let's go ahead and delete these plots. Now, We're going to go back and set the noise to 0. Run the simulation again, and you'll notice that the output of the demux being corresponding to the peak of the match filter is right at where the eye opens. Now what we're going to do is demonstrate the phase of the demultiplexer. So let's go ahead and change its parameters. Notice that the phase is 0. Let's set the phase to 5, which is offset from the peak of the match filter. So it's offset about 5 samples, so we're around this region here. And let's see what the effect of that is on the demux output. So let's go ahead and run a simulation. So even though the eye diagram obviously doesn't change, we're sampling around here, and you'll notice that we're not at the peak anymore, and occasionally we get different levels, which indicates that we're not sampling at the right phase. In a typical digital communication link, you would have to do timing recovery and actually estimate the correct phase for sampling where the match filter peaks. Of course, we're manually setting that in this digital communication link. We have other simulations that actually do that and estimate both the timing, do timing recovery, and correctly sample at the right phase automatically. But that's a topic for future discussion. Okay, let's go ahead and save this topology. Actually, let's go back and change this to 0. And we verified that 0 in fact is the peak of the match filter, which is exactly where we want to be. Let's save that. Let's do another run. Verify that the plot is okay. We're at the peak of the eye. Let's delete these plots. Okay. Now the next step is to show how we can actually measure the bit error rate. After we do the decisions, the samples over here are the original, they're estimates of the original bit stream that were sent. Now the bit streams themselves, although here they're between their binary data 0 and 1, the coder maps them to plus and minus 1. The slicer maps them also to plus and minus 1. So in order to do the bit error rate, we need to compare the symbols that were transmitted with the symbols that are received. Now in order to measure the bit error rate, we need to add the block called error count. Actually, we're going to use another block called error count FAP, which stands for file append. And there's a benefit to that because this particular block allows us to actually not only measure the bit error rate but also to append it to a file. So if you do multiple simulation runs, the results when you change parameters are all tabulated in a single file. Now when we use this block, but let's go ahead and change the parameter. Let's look at the parameters. First of all, there is a number of samples that you want to ignore because of transients in the simulation due to, for example, adaptive filters converging and so forth, and filter responses, etc. You would like to skip the transient period before you actually measure the bit error rate. So we're going to skip over the 30 bits. The next parameter basically indicates after how many samples you want to record or actually report bit errors, because when the events become rare, you would actually start reporting them. And the final parameter is the file name that's going to accumulate the bit error rates between multiple simulation runs. So let's go ahead and save that. Now the next thing is we have to go back to the coder and get the original symbols that we're going to compare with the demodulated symbols in order to get the bit error rate. So we're going to add a delay block. I'll explain why we need the delay block. Let's go ahead and add that. Let's get rid of this. We're going to add the delay block right over here. Now we need a delay block in order to align the transmitted symbols with the received symbols. Notice that when the transmitted symbols go through the whole communication link, due to the channel, the response of the filters, various delays, you need a delay in order to align the two symbols, the symbols with each other. Let's go ahead and make this connection. Now it turns out that that delay for this particular simulation turns out to be 12 bits. So we'll just type in 12. Now we need to go and connect the delayed original symbols to the error count block, and we have to compare it with the demodulated symbols. Let's go ahead and connect that up, and we have the actual setup in order to do and measure bit error rates. Let's go ahead and save this topology. Now let's go ahead and make sure that our noise is 0. We have no noise. We already have an ideal channel. Let's go ahead and run a simulation. Okay, you'll notice that the eye is quite open. There's no noise. And down here you'll notice that the bit error rate is reported, and we have 0 out of 90. Notice that there were 12 errors, but these are errors that occurred during the transient period. We're ignoring 30 of them, so our bit error rate is 0. So let's go ahead and add some noise. And even though we're going to add quite a bit of noise, the bit error rate is still quite low. Let's add a variance of 0.4. Run the simulation. You'll notice that the samples that are at the peak of the match filter have noise and vary quite a bit. The eye is obviously very distorted, kind of closing up as you add more noise. But notice that the bit error rate is still 0. And what we need to do, of course, is to generate more errors is to increase the number of bits. So instead of generating 128 bits, let's generate 10,000 bits. Let's get rid of these plots. Let's run the simulation. So now, of course, we got 10,000 points, and you can see from the plots that there are many points here. And the eye is obviously closing quite a bit, but still it's open enough that the decisions result in a bit error rate of 0. So let's go ahead and delete these plots, and let's increase the number of points to 100,000. Hopefully we get some rare events in which we have a bit error. Okay, now we have obviously 100,000 bits that were generated. Now the bit error rate is 2 times 10 to the minus 5, and you'll notice that with Capsim we can efficiently simulate communication links because it's fast and in C, and generate bit error rates for rare events for modeling communication links that, for example, have very low bit error rates. The add noise block generates random Gaussian noise which is pretty good in terms of generating rare events. This concludes this part of the tutorial, and later on we're going to explain how you can couple this whole communication link to the Tickle script in order to set up iterative simulations and generate tables automatically of the bit error rate versus the noise or signal to noise ratio.